You're traveling at a constant speed in a straight line. In physics, this is called a constant velocity. If the windows were blacked out, could you tell that you're moving? No. Is there some way, with some sort of measuring device, you could measure the fact that you're moving at a constant velocity? Relativity, or relative motion, tells us you cannot measure it. In this video, we will show that you can. To demonstrate this, we will first carry out some experiments. Tim and I will be driving our rocket car. Simon on the right is going to be the observer. The aim is to measure the amount of force that applies as the car carries out two different maneuvers. The first will be driving in a circle at a constant velocity. The second drive will not be at a constant. Using a load cell. Fastening the cell to the car's inner bodywork. Then attach a mass to the top of the cell. The load cell sends out a changing charge that is proportional to the amount of force being put on it. This information will be shown on a graph. Due to centrifugal acceleration, the load from the mass pushing against the load cell remains at a constant value. Our observer, from outside and inside the circle of rotation, knowing the distance of the mass from the center and its velocity, works out the same result as the graph. The second maneuver. A blue ball is moving across the track at a constant velocity. The observer observes that the car is accelerating and decelerating to catch up and then fall behind the ball. From Simon's observation position, we are not at a constant velocity. The readout from the graph and our drive experience confirm Simon's observation. As the car increases and decreases in speed, the curves represent the force change at each point on the load cell. From this point to the top, the mass is decreasing in velocity, going in this direction. From the top to the bottom, it's then increasing its velocity. We'll go into more detail on this at the end of this section. The observer Simon. By changing his position, can he change the readings from the load cell? No, that's impossible. He is only the observer, he has no influence on the mass in the car. Simon's new position cannot change the readings on the graph. The only thing that has changed is what he can observe from that new position. From this point, his observation calculations will be totally different than before. Relative to him, his new calculation will look like the car is just rotating at a constant. That the readings on the graph should be straight, with no deviation. The observer Simon makes two different calculations. Only the one on the left matches the readout from the load cell. The relative motion analysis on the right, for the mass on the load cell, is incorrect. Simon is deceived into thinking this is the reality for our mass. Looking at the screen, do you see constant velocity? No. Two accelerations are happening at the same time. The rotation part of our motion, we get centripetal acceleration, giving us a constant centrifugal force of the mass against the load cell. This is represented by the red dashed line on the graph. As seen from your observation. As we are also moving in this direction, the mass now has an ever-changing rate of acceleration. This change gives us an ever-changing force on the load cell, in addition to the rotation force alone. The combination of both accelerations give us the readings we get on our graph. This happens to any mass on a rotation, when the rotation center is moving at a constant velocity. The observer's position cannot change this. And now the apparatus. Moving at a constant velocity is a person contained within a sealed compartment with one-way glass. The apparatus consists of two load cells, each with the same mass placed at the top. The load cells fasten to the rotating platform at the edge, placed opposite to each other, to balance the system. The platform's rotational speed is set to a constant value. This can be adjusted, if needed. As with the car, just rotating, the graph is showing a constant force from the mass against the load cell. The container is now moving at a constant velocity. We now see the two telltale curves on the chart. The peak of each curve indicates the line of travel. The direction along that line cannot be determined. If the constant velocity rate was greater, the dynamics of the two curves would change. It should be possible to gauge the actual velocity by analyzing the shape. By changing position, an observer can only change their perception of what is happening. They physically cannot change anything. The observer from this position in space observes the rotating apparatus placed here. It is also moving at a constant velocity with the ground at over 500 miles per hour. Knowing the mass's distance from the center of the apparatus and its velocity, they calculate the same readings as the graph. When the observer changes position, the graph's readout remains the same. Only their perception of what is happening to the mass changes. If we see no curves on the graph, the ground is not moving. If it's not moving, we don't live on this.